This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everybody. And this week we're going to change topics slightly. So last week we were talking about phylogenetic tree reconstruction. And for this week, we're going to talk about a very trendy topic in computer science and bioinformatics and computational biology in general, which is machine learning. Have anyone worked or currently working with machine learning in this room? Or is aware of? Okay. Just a few people. Yeah, so the way we're going to approach this is it's a very vast subfield, and this is not a machine learning subject, but we're trying to cover the basics so you actually understand and know the tools you can use on your own projects. And this is going to run for 3 different weeks and scattered across the semester. And we'll start today with something that we already started previously, which is clustering. So it's a part of machine learning and it has to do with grouping similar items. But let's start with a very basic concept, which is learning. What's learning? Learning is basically any process by which a system, biological or not, improves performance from experience. Okay? So keywords here, performance and experience. And in terms of a computer, what does it mean for a computer to learn? And we can ask a few other questions that are related to that one. For instance, why would we want to teach a computer how to do things? And how do we get them to learn? Okay, and the basic answer for that is we want computers to learn when it's quite too difficult, too expensive to program them directly to perform a task. I want them basically to understand how the task needs to be performed instead of directly inputting a sequence of commands that will render the output I want. And basically what we want to do is get a program. It's a computer to program itself by showing examples of inputs and outputs. For instance, we want to write a parameterized program and let the learning algorithm find a set of parameters that best approximates the function or behavior we're interested in. And for instance, this machine learning has been quite successful, especially in the current days in image recognition, especially given the rise of deep learning. And for instance, one might be interested in identifying different characters. And there are very different ways to write down numbers. Right? Instead of just summarizing and writing down directly a program that can identify all possible ways, I can just input a data set with different numbers and then get the algorithm to find out what are the patterns that represent each number. And this is quite a difficult task even for us. If you look at this, we have different ways to represent the number 2. If you ask me, this 3 looks like a 2, this 6 looks like a 2 as well. So machine learning is a very, very interesting approach to identify hidden patterns in the data, okay? And a very powerful one. And the term machine learning was coined quite a while ago, in 1959 by Arthur Samuel. And at that time, he said that machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. So a different way to say what I just said. And this was revisited 40 years later by Tom Mitchell. And he defined machine learning slightly different. So machine learning for him is a study of algorithms. So all comes back to algorithms that can perform a given task with a given performance, and that performance improves with experience. And so for him, a learning task is given by 3 aspects. So a performance metric, a task, and experience. Let's try to think about it these days. Let's say you work in a weather prediction agency and you want to build a predictor that will say whether it's going to rain or not tomorrow. So raining or not tomorrow is your task, is your predictive task. So it's let's say it's a qualitative approach. I just want to say whether it's going to rain or not, okay? Our performance could be how many times we get this right. Let's say we have two possibilities. It's going to rain, it's not going to rain, and over time we can collect a metric that will say how accurate our predictor is. And in fact, this metric in this instance is called accuracy. So this is the percentage of correctly classified items. So then we have a task, a performance, but how do we learn to perform that task is given experience. And experience in this case could be interpreted as historical data. So that's one of the bases for supervised learning, which is part of machine learning, which is, for instance, in terms of this weather predictor, I can use historical data, for instance, the period of the year, how much rained or not rained during the same period in previous years to use as evidence to train this algorithm. And then we have the three aspects: previous experience, a given task, and a performance metric. And basically, we can divide machine learning, the whole field, into two main ones. Of course, these days we'll have more categories that we're not going to approach during this subject, but without laws of generality, we can consider two: unsupervised and supervised learning. And unsupervised learning will have to do with algorithms that operate in unlabeled examples. And this is more related to data description. And the main task for unsupervised learning is clustering. Let's say you have a set of items. It could be, for instance, your protein sequences. And you have a way to represent or extract characteristics or features from these sequences. And you can plot them. Let's say they're all numerical, and you can plot them. What you're asking is how this data is organized without labeling them. Right? So it's a natural organization of the data that you're asking without having the actual description of any of the sequences. While supervised learning will have a different approach. So algorithms are trained on labeled examples. So let's say for each sequence, I know this sequence belongs to a specific functional class, and this set belongs to a specific functional class, different one. So you have a classification problem. And in this way, supervised learning has more to do with function approximation. And the main two tasks for supervised learning are classification and regression. And the main goal for supervised learning is, given a new data point in that same feature space, I want to ask the question, is that blue-green sphere or that red cross? So understanding what would be this one. And this is basically the main goal for supervised learning in terms of classification. And the main difference from classification and regression is the outcome you're interested in. Classification, we are interested in categorical values. For instance, either this class or that class. It's going to rain, it's not going to rain. While regression, we are interested in a numerical value. So it's a quantitative approach. Instead of just saying it's going to rain, I'm going to say it's going to rain 10 millimeters per square meter. Okay? And that's the main difference between the two of them. And of course, we'll have different algorithms and different approaches for your different classification tasks. But for those, you already know in advance what are the answer. So you use that fact that you know the answer to train an algorithm to predict new data. Okay? For instance, let's say you have a data set of sequences that you extract information from, and they are all labeled based on their function. Given a new sequence, you want to predict this function. Okay? And you need the historical data to do that. And clustering, well, cluster in terms of unsupervised learning is basically the organization of unlabeled data into similarity groups. And we call these groups clusters. And basically, a cluster will be a collection of data items which are similar between them and dissimilar to data items in other clusters. In a sense, then, the intuition behind clustering approaches would be we will try to identify or cluster items in order to minimize the distance inside the cluster, so minimize intra-cluster distance. We want then these clusters to be homogeneous as possible. And at the same time, we want to maximize the distance between clusters. So we want two things in clusters. Cluster separation, they are as far as possible from each other, and they are homogeneous as possible within each cluster. This is the basics for clustering. And why is clustering useful? One of the main aspects of clustering, it does not require labels, and especially in biology sometimes is not an option, because identifying the labels experimentally might be costly or time-consuming. If you think about characterizing a protein function experimentally, that costs a lot of money, that takes a lot of time. If you have an unsupervised learning approach, you can then basically skip that part and try to understand how data is organized, even without the labels. And so, therefore, clustering is quite important and quite useful for discovering patterns on your data and how they are organized. And in other words, it's quite interesting to discover hidden structure of the data. And clustering, of course, it has many, many different applications. We covered a few already. One of the main ones in computational biology, of course, is phylogenetic tree reconstruction. If you recall previous lectures, we talked about agglomerative clustering. So we started basically with each sequence or species in a separate cluster, and we start grouping them and forming a hierarchy. There are other examples of clustering applications, for instance, clustering samples, and this is quite common on gene expression data. Let's say you have different conditions in a panel of genes, and you want to cluster genes that have similar expression, that let's say they're more or less expressed, and that will help you visualize what's going on between different conditions, so you can cluster them based on that value. You can do exploratory analysis or data visualization, which is quite useful when you don't know what the pattern looks like. And in that sense, clustering could be even a preliminary analysis to further analysis down the track. And in terms of visualization, one interesting way to visualize data with agglomerative hierarchical clustering is called a heat map, where you try basically to separate your data in things that are more similar to each other. And that could help you explain the biological pattern you see. Clustering is also very important for data compression and sampling, and this has been quite important, for instance, for image analysis. And the main idea for data compression is we want to replace the data or replace many data points with a few representative ones. And for instance, on image, we can represent many colors as a few representative ones. Okay? So it's the same image using only 10 colors, 3 colors, and 2 colors. In that sense, we're using less information and using different levels of details on that image. And what it does, it's you have basically, you spend less space saving it. And clustering is quite important for sampling as well. And let's say you're working on a database of sequences, and you have sequences there that are very similar. So one pre-processing step you can actually perform is ask the questions, how do you select a representative subset of those that have more or less the same distribution? One thing to do, for instance, is group or cluster sequence by similarity. Okay? And clustering is quite important as well in a recommender system in collaborative filtering. And this is based on, let's say, we cluster users in social networks and recommend stuff they might like. And this could be in 2 ways. For instance, clustering similar users. Let's say these 2 users, they read more or less the same content. And given that this one read this article, you might say that this one might like it as well. So clustering on the user level. Or you can cluster contents. So given that this user reads a lot of this, you can cluster similar articles and make recommendations for them. So clustering is really, really broad technique that has been used over time quite a lot. And there are 3 main ingredients for clustering. So the first ingredient is one that we exhaustively discussed, which is trying to find the similarity or the similarity metric in order to compare the items of the clustering. So most of the clustering algorithms will deal with distances. And of course, we always get to the point at asking what does similar mean. And we've discussed Euclidean distance. There are also other types of distance, edit distance, Manhattan distance. And the main lesson here is that the clustering, the resulting clusters will be dependent on the similarity metric you choose. It will be depending on the feature you use to cluster on. And the second ingredient for clustering will be then a function to evaluate the quality of the clusters, okay? And remember that we want two things. We want intra-cluster cohesion, or we want homogeneous clusters, and we want inter-cluster separation. So we can try to derive different metrics to optimize these two. But at the end of the day, clustering might be quite subjective. So it still requires expert knowledge to evaluate it. And of course, you need the third component, which is the actual clustering algorithm, which will be able to perform differently based on how your data is distributed. For instance, you can have, let's say we consider these sets of points. One potential clustering is just dividing them in two groups. But maybe we can divide this group in two, or we can divide this group in two. What's the best one? It depends on your criteria to evaluate the clusters and your knowledge on what they mean. So the clustering algorithm, what it will try to do is try to optimize the evaluation function we define. And then we might need to ask the following questions. How many clusters do we have in your data? And we basically could have two approaches for that. We predefine the number of clusters we want. For instance, you know your data enough that you know that you expect two different groups in your data. Or you can ask the question, what's the best number of clusters that optimize intra-cluster cohesion and inter-cluster separation as well? And in that way, optimize the number of clusters you get. But in essence, clustering is quite subjective, and there are different possible ways to go about it. Let's just consider this example. So we have the Simpsons characters there. How would you cluster this set of objects? I'm not giving you the features. So if probably we'll come up with multiple different ways and equally plausible ways to cluster them. How would you cluster them? You in blue, front row, that is not looking at me. Him. How would you cluster them and why? Heights, yeah. You basically pick a feature and say above this height is one group, below this height is another group, and another way. Gender, yeah. You can say, let's say, we cluster the males on one side, females on the other side. There are so many different options. That depends on how you represent your data. Let's say we'll cluster the Simpsons family on one side, school employees on the other side. Let's cluster who can play an instrument on one side, and everybody that can't on the other side. Let's place children on one side, adults on the other side. So there are many, many different ways to do clustering. And it's up to you to decide what's more appropriate for your data, okay? And that depends on the information you're using to represent your data. And clustering approaches, they can be divided into main categories. The first category is subdivided into two. So we can have exclusive clustering, meaning the data points belong to one and only one cluster, like is showing here on the right, okay? And you can have overlapping clustering, okay? The data points may belong to different many clustering. This is quite common when you have a probabilistic approach, okay? And the other classes of clustering approaches that are also divided into, we have hierarchical clustering that we already described. So we will assign points to nested clusters. And we can get all possible clusters for a given cutoff metric. Let's say we first define all the hierarchy of the given items we're studying, and based on a given metric, we could end up with 5 clusters if we want them to be very distinct and dissimilar, or we can end up with 2 or maybe 3. So choosing the right metric is also important to defining the number of clusters in hierarchical clustering. And we can have partitional clustering, which will basically split the points into flat, independent clusters. And then we have to answer the question, how many? Is it 2? Is it 3? And it's quite important to define that. And coming back to the 3 main components of clustering. So we had to define a distance metric, we had to be able to evaluate the quality of the clusters, and we have to have actually the clustering algorithm which will optimize this objective function. So let's start with distance metrics. So it's the first ingredient for clustering, and many hierarchical and partitional clusterings, they actually work based on pairwise similarities or dissimilarity metrics. And the one that we are quite familiar is the distance matrix, okay? And actually, the distance matrix, in order to be a metric, or any value to be a metric, you need to satisfy the following properties, and that's quite important for clustering. The first one is being non-negative. So every single distance from a given element from A to B needs to be greater than 0 or equal to 0. The other important property for metrics is identity, meaning that distance to itself is 0, meaning, of course, that the diagonal is 0. Symmetry, which means distance from A to B equals distance from B to A, meaning we have a symmetric matrix. And triangle inequality. So given 3 points in space, A, B, and C, the distance from A to C is always less than or equal than the sum AB, BC. Why is that? If you consider the Euclidean space, the space we're in. Why this is always true? It needs to be, by definition. When we consider any 3 sets of points, this always holds. Why is that? And yes? This basically has to do with the fact that what's the minimum distance between 2 points in space? It's a straight line, right? Therefore, the only way for this value to be equal if they're collinear. Otherwise, it's going to be larger, okay? And these are the 4 properties that we need to have a metric. So you can pick and choose your metric, and as long as it has these 4 properties. And we talked about Euclidean distance, which is the ordinary distance used in Euclidean space, which is defined not only for 2 or 3 dimensions, but for d dimensions, right? So if we represent our data as a d-dimensional vector space, we can always calculate Euclidean distance. It could be 100 dimensions, 1,000,000 dimensions, okay? We basically do the square of the sums of never mind. It's quite difficult to say that, yeah. But we can also have, for instance, the Manhattan distance. Have you heard of the Manhattan distance before? It's also called the city block or the taxi cab distance. So instead of defining the shortest distance between 2 points as a straight line, we can only go left to right and up and down. Okay? And this is quite important depending on the system you're working on. And this is valid as well for a multidimensional space. And we have discussed extensively editing distances. Hamming distances, including only single error substitutions, Levenshtein, which also includes indels. And there's also a third one, which is not considering substitutions at all, and in this case is called longest common substring, which I'm only considering insertions and deletions, okay? And you can pick and choose the most appropriate one. And you can even calculate distances from k-mers, if you recall from a couple lectures before. So given 2 sequences, the k-mer then is a word of size k. We do a sliding window on the sequence, and we account the different words we come up with, okay? And one way to use that information to calculate distance could be, for instance, representing this as a vector and calculating the Euclidean distance, or we can calculate a k-mer distance as the proportion of unique k-mers between them. And that's called actually Jacquard index, which is quite used as well. And the Jacquard index is basically the number of words or k-mers that are in common divided by the number of k-mers or words that are in total. Okay?
Is it the same? Is it the same? The Jacquard index and k-mer distance?
I'm just calling that let's consider a k-mer distance like this, and in this case, it will be Jacquard index. I could come up with a completely different k-mer distance and call it, that's my k-mer distance. They are not synonymous, okay? Jacquard index is this. K-mer distance, you can say my k-mer distance is Euclidean distance, okay? My k-mer distance will be a edit distance, for instance, okay? And this is Jacquard index. And there's a trick here as well. So careful with the word distance and index. So Jacquard index measures similarities, right? So the higher the value, the more similar they are. However, the most similar, the smallest the distance, okay? So what you need to do is correct it. So Jacquard index is the proportion of those that are in common, so it's a similarity metric. And if you want a distance metric, you have a Jacquard distance, which is 1 minus the Jacquard index. Is that clear? Okay. And again, so the cluster's results, they are crucially dependent on the measure of similarity we choose, so it's extremely important to choose an appropriate one for your problem. And of course, there are other possible distance functions. For instance, there are correlations that we can calculate, Pearson and Spearman correlation between random variables. We can calculate cosine distance that will basically assess similarity between vectors. Let's say you're just assessing whether the data is pointed to the same direction, regardless of magnitude, and then you can calculate, for instance, the cosine distance, or you can have a distance in a graph that you could define, for instance, as the shortest distance between two nodes in the graph, okay? Which is quite important for clustering in network analysis. Let's say you're assessing KEGG networks or protein-protein interactions networks, and you want to cluster nodes in the network, then you can, for instance, consider a distance that is relative to the graph. And we'll start then talking about one specific partitional clustering algorithm, okay? So we go back to partition. So we're interested in splitting points into a flat, independent cluster, and of course we need to answer the question, how many? So partition clustering in general, they are non-hierarchical in construct with, of course, hierarchical clustering, and each instance is placed exactly in one of k non-overlapping clustering. Since only one set is the output, usually it's asked for the user to provide the number of clusters k. And just recalling the ingredients for clustering, we need then to, for partitioning clustering again, a similarity metric. We need to be able to evaluate the clustering, which we'll call objective function, and the actual clustering algorithm. And the first algorithm we're going to discuss is called k-means. So k-means is a very famous clustering algorithm proposed back in '67 by McQueen. It's a partitional clustering algorithm. And it has a few assumptions. For instance, let's assume the data is in Euclidean space. Of course, you can use different space. You can implement k-means to work in different distance metrics. Let's consider for now Euclidean distance. And we'll, of course, based on the name, we're expecting a k value as an input, which will be the number of groups we'll have as output. And also, let's assume to start off with that the k groups will be randomly located and centered on cluster centers, which are centroids. So basically, this is the initiation step for k-means. Let's randomly select k centroids, okay? And basically, k-means will have two steps, two very simple steps. The first one is the assignment step. And the assignment step, I'm going to assign each data point to the closest cluster or to the closest centroid. Okay? And this will divide my data into k clusters on the first round. The second step is the refitting step. Okay? And the refitting step is we're going to move each cluster centroid to the center of gravity of the data it's assigned to it. Okay? And we'll keep iterating through these two steps until we reach a stopping criterion. That could be, let's say, no points or clusters are reassigned. Oh, yeah?
So the center is always the data point in the cluster?
I couldn't hear you, sorry.
Oh, so the center of each cluster is always the data point in the cluster?
No, not necessarily. So to start with, we choose a random point. It doesn't need to be a data point. Okay? For instance, let me see if I can show you graphically. I'm going to show you graphically, actually. So basically what we're going to have is, let's say you have a group of 3 points in space. You're going to select as a centroid any point in that area. Any point in that area. It doesn't need to be a data point. Okay? And the actual value for that point will vary. And that's why it's called here a center of gravity. It's a mean. So it's basically the mean value for the set of data points. So it could be a data point, but most of the cases it won't be. Is that clear? And we have a stopping criterion. So basically what we're trying to do with k-means is minimize the distance between points and centroids. So let's consider x the points we have, and the point that represents the centroid. We want to minimize this distance. Okay? K-means algorithm, which is quite simple, it will run like this. Let's say we have this distribution of points here. We're going to select 2 random points to be assigned as centroids. Let's say one is here, the other is here. That's our initiation step, right? And then what we're going to do is we're going to find the closest cluster we have, or the closest centroid we have, and we are going to assign each of the points to that cluster. Okay? Which is basically, in this case, which is just a 2-dimensional and very simple example, is just drawing a line between them and finding, well, these in blue are closest to this centroid, these in red are closest to that centroid. And this is basically the cluster assignment on the first round. Okay? Next, what we're going to do is we're going to recalculate the centroid for blue and red. So the centroid will move to here and here. This could be exactly inside the data point, but usually not really. It doesn't have to be. So this is basically the center of mass or center of gravity of all points of that cluster. And then we refit the centroids. And once refitted the centroids, what we're going to do is we're going to basically recalculate the closest cluster. So for each data point, we're going to reassign them to the closest centroid. And of course, the clustering distribution will change. And again, we'll refit the centroids, and we'll keep going until there is no change in terms of centroids or in terms of the cluster assignment. So no points move from one cluster to the other. Okay, so basically initiation steps, then 2 steps until we reach a stopping criterion, and that's k-means. Okay? So there are a few interesting properties for k-means. For instance, k-means is a heuristic. And I haven't mentioned that, but finding the best data partition you have requires extensively enumerating all of them. And the number of partitions of size k for a given data is exponential. So in order to do that, we assign points to the closest centroid, and that's basically the heuristics for k-means. And the k-means objective function will decrease at each step, which guarantees convergence. So the program will stop after a few iterations. But of course, it has its drawbacks. For instance, when you have a situation that you actually asked for just one cluster in that region, when you should have 2. And when you have 2, that actually it looks more like a single cluster. One important fact about k-means, it may not converge the optimal solution, considering it's a heuristic, but it may reach a local minimum instead. So, and this can change depending on how you initialize the centroids. So what we try to do with k-means is run it multiple times to assess how stable the clusters are. And in terms of time complexity, k-means is O of tkn, where n is the number of data points we have, k is the number of clusters, and t is the number of iterations. So k-means usually converges fairly quickly, so t is considerably lower than n, and we usually clustering in a number of clusters that is considerably smaller than the number of points we have. So you could almost consider k-mean linear. So it's relatively efficient in that way, and very simple, very widely used. Very, very simple to implement as well. So simple I might ask you to implement it for me. Maybe during the exam. Maybe not. Okay? It's quite simple. And of course, the main limitations of k-mean is it's only applicable when the mean is defined. When is the mean not defined? The mean is only defined when we have numerical data. When we are counting k-mers, we have the actual number for which we can count an average. How do you average a cellular location? How do you average a protein name? So when you have categorical data, you can't use a distance metric, okay? So it's one of the limitations. And of course, you need to specify the number k, the number of clusters in advance, which is also takes its importance. And also k-means is quite sensitive to outliers, as I'm going to show in a bit. And it's not suitable to discover clusters in non-convex shapes. So in terms of outliers, if you look at this figure on the bottom here, you have two natural clusters here. And you have an outlier that's quite far away. And the mean, it's quite sensitive to outliers in the sense that if we choose to cluster this item, it will go to this cluster, for instance. The mean will be dislocated quite a lot just because of one element. You could have a cluster with 1,000 elements. If the distance here is too high, then you mess up with the whole clustering. And k-means a struggle with non-convex shapes as well. So if you look at this, it's a natural way, just looking at the density of the points, to cluster them in two groups, this one and this one, while k-means won't be able to get that because we're considering distance in a straight line. So one of the questions for k-means is how do we best initialize the centroids? And there has been different approaches to try to improve k-means. So poor initialization can lead to slow convergence, so taking a longer number of iterations to converge, and converging to a local minimum instead of the global one. And there is, for instance, one algorithm called k-means plus plus that tries to improve that in the way we choose the initial centroids. Did anyone? No. And how do we know whether we found a global optimum or not? Well, what is usually done is that we run k-means multiple times. It's such a quick algorithm, we can effectively test how stable the clusters are and check for stable convergence. If I run it 100 times and every single time I have these sets of proteins, for instance, in the same cluster or not. And how do we choose the number of clusters? We can try different combinations, and one of the criteria used is usually what's called, when we look at the objective function and it sharply increases or decreases. This is also called the elbow criterion. So you have something like this. The distribution starts to level out. The elbow will be next to the corner. And you can also use external validation if that's available. So for instance, you can have label data to evaluate your clusters as well, even if you don't have labels for every single data point you have. And when k-mean fails, then k-mean will fail for clusters of different sizes. If you have a really large cluster followed by smaller ones, it might fail to identify that. K-means might also fail for clusters of different densities. While we could naturally see that we have 3 different clusters there, k-means might struggle basically trying to divide this less dense cluster. And k-means, as mentioned, it's not appropriate for non-convex clusters and clusters of different densities as well. And in that case, we're better off with different approaches. And for instance, one alternative to k-means that actually attempts to make it less sensitive to outliers, which is a very simple change to the algorithm, is called k-medoids. And as I said, it's an improvement to k-means. And at the centroid for each cluster, instead of the mean, the actual center of gravity, we take the most central data point. So it's an actual data point instead of the average between, the mean between them. And that has actually a dramatic effect when you look at how it deals with outliers. And that's basically the difference between a mean and a median, right? So a mean will be quite affected by an outlier, while a median wouldn't be. And then basically the algorithm follows as k-means would be, so you will have the same optimizing objective function as k-means, and at each step we'll try to assign the nearest centroid, and we'll keep updating the centroid until we reach convergence with the most central point instead of the mean. And this makes k-meadows considerably less sensitive to outliers than k-means. It's still not perfect, but at least in terms of outliers, it's less sensitive. And however, it requires extra calculation to find the most central point, which means quadratic calculation in terms of the number of clusters, because I need to find, given my cluster size, what's the central point there. And of course, we have other clustering approaches that we might discuss later on, which are density-based. For instance, we want to cluster points that are close and in a dense region. And this is one way to go around non-convex and arbitrary shapes of the clustering. So there are quite a few alternatives for density-based ones. And however, they still make use of distance between points. There are also probabilistic approaches that for each cluster will represent them as a parametric distribution. For instance, the Gaussian mixture models that will allow, for instance, for overlapping clusters, and we could have network-based clusters. Instead of distance in the graph, we'll count the edges and the connecting nodes, and we'll find regions in the network that are densely connected. For instance, this could mean in protein-protein interactions, these proteins that are somehow related functionally. And that's it for today. Thank you very much.